In science, we use a lot of quantitative data. That means data with numbers. In chemistry, we sometimes use very small numbers for sizes of atoms and small distances between atoms. And in chemistry, we use large numbers for how many atoms or particles we have. In physics, we use very small numbers for things like charges, especially when it comes to atoms and subatomic particles, and we use very large numbers, especially for distances like between stars and other celestial bodies. To measure these distances, we use a shorthand called scientific notation. In scientific notation, we have a non-zero number, followed by a decimal, followed by any other significant digits, which are digits that we care about, multiplied by 10 to the power of something. It depends on how many times we move the decimal point over to reach that non-zero point something, 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 something. In scientific notation, we consolidate these really big numbers. So we have a bunch of zeros here, but we don't want to write out all of the zeros. So what we do is we have our non-zero digit, followed by a decimal, followed by the rest of our digits that are not zeros that we don't need, multiplied by 10 to the power of however many times we move the decimal place over. Here we move the decimal place over, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. We moved it over 9 times, so 9 is our exponent. Here, we move the decimal place the opposite direction. We want it to be non-zero number, point rest of the numbers, multiplied by 10 to the power of however many times we moved it. Since it's a small number, it's negative. So we go 3, 6, I spaced it out, you're welcome, 7, 8. It moved over 8 times. Since it's a small number and we moved the decimal point to the right, our exponent needs to be negative. A negative exponent means it's a really small number. A positive exponent means it's a really big number. Here we have a really big number, 602 hexillion, which is also a mole in chemistry. Happy day. We have a bunch of zeros here, so we're going to have our non-zero number, decimal, other numbers that we care about, multiplied by 10 to the power of how many times we moved the decimal point over. So we moved it over 3, 6, 9, 12, 15, 18, 21, 22, 23. We moved the decimal place over 23 times to get this 6.02 number. In scientific notation, it's 6.02 times 10 to the 23, which is Avogadro's number, or a mole. Quickly again, we have 29 million. That means you move the decimal place over 1, 2, 3, 4, 5, 6, 7 times to get it non-zero point rest of the numbers. So 2.9 times 10 to the 7th. So here I have another example. I put some spaces in my decimal points just so I could find my place easier. Now I need to find my first non-zero number, which is the 2. So I'll have that number, decimal place, the rest of my numbers, multiplied by 10 to the power of however many times I moved it over. So let's see, I moved it over 3, 6, 9, 10, 11 times. So since I moved it over 11 times, 11 needs to be my exponent. Since it's a really small number and I moved it this way, my exponent is negative. So it's 2.3412 times 10 to the negative 11th. See, over here I moved the decimal point this way and I have a positive exponent. So move it to the right and you get a negative exponent. To the left, you get a positive exponent. Because of scientific notation, we can use the same measurement to measure something very small and something very large. In science, our base measurement is meters. So using scientific notation, we can use a meter to show how small an atom is and how far it is to the nearest star. It's the sun.